welcome everybody to the first GSQ UQ webinar, collaborative webinar series for 2023. So I'm particularly excited today to be able to say that we have a guest organizer, Dr. Renjie. I don't even know how to pronounce your surname, Renjie. Is Renjie Zhou, or you're on mute, Renjie?
It's Zhou. I think
Zhou,
what you said
okay.
was perfect. Yeah.
We always just say Renjie, but he's a fabulous collaborator of the GSQ within the University of Queensland, and we love working with him. So Renjie has pulled together the outline for our first webinar for this year. Before we get going, I'd like to respectfully acknowledge the traditional owners of all the lands on which we meet today around Queensland, around Australia and around the world. We do have an international lineup, so there might be people from overseas joining, and we know we have an international reach. So it's very important to acknowledge everybody wherever we are. I would like to acknowledge their elders, past, present and emerging. And I also recognise those whose ongoing effort to protect and promote First Nations cultures will leave a lasting legacy for future generations. Right, now, the lineup for today, I'm going to leave to Renjie to discuss, but you can see them on the screen now, and Rick and I are here as backup more than anything today, so which has been really nice. And I'd like to congratulate Renjie on bringing together such fabulous speakers for our session on geochronology in mineral discovery. We have also got the opportunity to share with all of you the timetable of webinars for the year for 2023. So Evan Marshall has shared that in the chat, and you can all download that, and of course we'll share that through various means. And I think the links, Evan, are the links included in that as well, or just the... Anyway, we can come back to that.
Mm-hmm. Yeah, the links will be there, yeah.
The links are there, fantastic. All right, so if everybody could use the Q&A function at the bottom of your screens to ask questions, and we can curate those at the end of each presentation. You're welcome to make comments in the chat, but we do like the questions to go in the Q&A, but we'll do our best to stay on top of them. And you feel free to write questions throughout the presentations as you think of them, and then we'll come to them at the end. All right, well, over to you, Renjie.
Thank you, Helen. Welcome, everyone. This is a very exciting seminar series event. As Helen said, my name is Renjie Zhou. I'm a senior lecturer in geochronology and tectonics at UQ. It is very exciting today. We have a wonderful lineup of speakers today, starting with Dr. Olierook from Curtin University. He will give an overview on this variety of geochronological tools we can use to determine various processes related to the accumulation of mineral systems or the formation of them. And then we're going to move on to Dr. Belousova from GSQ, from a sort of government perspective, looking at what is the exciting strategic plans, exciting initiatives within GSQ that lead to the understanding of mineral systems. And then we will have focus on the recent techniques brought us by this talk brought us by Dr. Redaa. He will talk about this new development in the laser ablation space. And then in about an hour or so, we will have Dr. Doran zooming in from Ireland. She will bring in more of a user's perspective and, having some examples telling us how we can use geochronology together with other tools such as geochemistry, stable isotope geochemistry, to better understand mineral systems. So without further ado, I would like to invite Dr. Olierook. Could you share your screen, Hugo? Then he will start talking about this first.
Give me 1 sec. Let me just show you the screen.
Yeah.
1 sec.
It's coming up.
Right. Can you all see that?
Yeah, we can all see that. Fantastic.
Fantastic.
It's all yours, Hugo. Yeah.
I'll stick my little laser pointer on. Thanks for the fantastic introduction, Renjie. Can you all hear me all right?
Yes, we can.
Yes, fantastic. So, like Renjie said, I'm going to give you just a very a brief overview, if you like, particularly if you've never really worked with geochronology before, but really tailored to the minerals industry. So let me just get started. What is geochron? Is really anything that measures the age of Earth materials, and provides a temporal framework from which a whole bunch of other geoscience data can be, I guess, placed into it. It's concerned with the timing, the rates, and the durations of processes. So from a mineral exploration perspective, we're really sitting in sort of this general sort of corner of this wheel, if you like. And we're all familiar with, say, how the geological timescale has evolved. But unfortunately, in many cases, our mineral systems, particularly the ones in Australia, excluding maybe some of the eastern seaboard, do rely a lot in the Precambrian, and you don't have fossils for that. So you've got to try and rely on absolute dating techniques to try and establish the timing, those foundational, if you like, fourth dimension to your ore deposit models. Now, the petroleum industry, it's safe to say, has been doing this a lot better than we have over the past maybe century, if you like. But it's sort of in recent decades that the minerals industry has started to move towards this mineral systems approach. And I think it's a really good way of moving away from traditional models, and where we sort of package everything into, say, an IOCG or a banded iron formation, or something that has a finite number of elements that all seem to work together, and to really consider every ore deposit, every prospect, every region of exploration as a unique set of components. And those components include the sources of fluids and metals, some pathways, traps, and how these things are preserved. At all kinds of different scales, from, say, global scales, where we're looking at plate tectonics and geodynamic processes, right down to deposit scales, and even sort of pit scales of individual mines. And geochron plays, say, a fundamental part of that. Why it's powerful, here's just a few examples. You're able to build tectonic models, understanding how, say, that global scale, or at least that sort of tectonic scale, has evolved through time. You're able to sort of correlate stratigraphy across, and particularly as we start to move towards exploring undercover and areas where we might have some geophysics to correlate things across, but we might not have that direct outcrop. And let's face it, Australia is pretty terrible with outcrop anyway. In terms of the sheer area of outcrop of particularly of mineralized systems, we don't have a lot of it. So to be able to pull things across space is incredibly powerful. We can search for the correct stratigraphy. Let's say you've got a gold mineralizing event that happened here, and this is in the Yilgarn Craton in WA. That happened at about 2.64 billion years ago. We want to be looking for rocks that are at least older than that, because the younger ones, they're post that gold mineralizing event. And I understand this is quite a simplistic view of looking at the Yilgarn, but it's a broad kind of picture we can take from that. We can look at metal fertility through time. For example, if you're looking at magmatic nickel copper deposits, you want to have some juvenile crust that's just been extracted from the mantle. That might be the same for your gold mineralizing events. So you want to have, in this case, this is an epsilon hafnium map of the Albany-Fraser origin in WA. So Perth is somewhere here, Queensland is way off the other side of the country. But we want to be getting into these sort of red zones in here to be able to extract that nice juvenile crust straight from our mantle that could be rich in nickel and copper potentially. Or we can look at things at the grain scale. We can look at, say, certain vein systems, and we can look at trying to date different generations of vein systems. And I think Ahmad's going to tell us a little bit more, maybe not about this exact same study, but on similar studies and how we can use novel techniques to try and figure out I guess the complexities of mineralization and the multi-stage pulses that we can get there. Just in terms of say a complete back to basics aspect, geochronology is radioactive decay, and that's the principle, the underlying aspect of geochronology. And if we look at the periodic table in terms of elements, in terms of their number of protons and neutrons, stable nuclides have this balance, if you like, of protons and neutrons. Always a few more neutrons than protons. But as you start diverging from this optimum line, you start to have products that are unstable, and over some timeline that will decay to daughter isotopes via either alpha decay, in other words, a helium nucleus, beta decay, or gamma decay. And it's really particularly these top two in here that we're concerned with. And probably traditionally, we've been more focused on the alpha decays, things like uranium lead, but there's a lot more, at least efficient work that's been going on in terms of looking at beta decay systems like rubidium strontium. This is not minerals focused at all, but I always like talking about a few very young systems. I mentioned before that obviously everything has a different half-life, a different decay constant. So we can look at really young systems like cobalt nickel dating, which is a half-life only just over 5 years. We can look at things like probably carbon-14, which is probably the most, at least globally well-known dating system, which is used in a lot of archaeological applications. But quite quickly, you can appreciate that over time, let's say you take this cobalt nickel system, after 25 years, you're only left with about 3% of your initial parent isotopes. And to be able to get a robust age from some sort of sample media, ideally we'd have 50-50. We'd have half parent, half daughter to be able to measure both the parent and the daughter isotope equally, get the best sort of precision on those and get us the best sort of results from that. But quite quickly, as you start to have isotopes with very short half-lives, or even ones with very, very long half-lives, you're not able to measure them in as much detail as you'd like. Some of these really young systems, you can start to use for things like soil dating, in terms of, let's say, when you had this massive spike in carbon-14, delta carbon-14, if you like, which is carbon-14 over carbon-13. When you have big nuclear testing, you can use it to test. This is probably one of my favorite ones. You can use certain techniques to test how old a bottle of wine is. Now you can see, maybe difficult to see, but there's some scribbles on these wine bottles of a year, 1789, I think it says on this one. Is that really an old bottle of wine? Or somebody just poured it in there yesterday, made the bottle look a bit old and said, here you go, guys, $500,000 for this bottle. You can use it to study groundwater and its movement. You can use it to study gorge and cave formation, human migration, loads of applications. But none of these are really particularly pertinent to the minerals industry. So what can we use? Well, these are probably the most common. There are a few others than that, but really this is fairly comprehensive. And the reason we can use these isotopes and these systems using uranium, potassium argon or argon-argon as a sort of modification of that, rubidium strontium, samarium neodymium, thorium lead, rhenium osmium, and lutetium hafnium. These systems are powerful because they have relatively long half-lives. That means that by the time these minerals are formed, and particularly when we're looking at the Precambrian, but also into the Phanerozoic, these systems still have enough parent isotope left that we're able to measure that parent isotope to some level of confidence. And so these sort of systems range from about 700 million years towards as high as, in this case, 106 billion years. And so you can appreciate, for example, that even in young systems, things like samarium neodymium may not give you a great precision because you still had just very little time to start forming this radiogenic product, this neodymium. If you've only had, let's say you've had 500,000 years, if you like, of decay, then you're only producing 1/212th, if you like, of that system into your daughter isotope. There's a whole bunch of different techniques that people have used to try and measure these things, and there's constantly advancements in technology. I know at Curtin here we're getting a new machine specifically to try and say work on new techniques to be able to do in situ. For example, we might be able to do in the future rhenium osmium in situ. We might be able to deal with other beta decay systems. There's some classic ones. Certainly in the early days, really the only system that was around, at least since the 1950s, was thermal ionization mass spectrometry. It, to this day, remains the most precise way of measuring things, and I'll show you another slide to kind of illustrate my point. But since the sort of late 70s and early 80s, there's been a massive explosion in different techniques that we can use to try and measure things. We can use secondary ion mass spectrometry, so things like the shrimp or the Kamika models that exist, like the 1280 and the 1300. We can use a whole bunch of laser ablation techniques. We can use things like an alpha chron to try and measure helium isotopes. We can use noble gas mass spectrometry to look at things like argon, but even things like krypton and neon in a trace element sense. And we can go right down to the atomic scale and look at nanoscale problems. Things like, how does gold partition into pyrite? How is uranium stuck in zircon, and what does that tell us in terms of how lead mobilizes? So what do you use with that sort of wealth of techniques that you've got at your disposals? And I'm very privileged to be here in WA, but in Australia generally, we have a phenomenal infrastructure, I guess, wealth here that other countries in the world just don't necessarily have. I complain when I have to drive across the river to get to the University of Western Australia just to use one of their machines when it's 20 minutes down the road. But really, it's such a fantastic place to work in geochronology that the minerals industry has sort of at their disposal. You contact any of the sort of proximal universities, so you'll find those instruments that they can use to date your rocks. But what do you use? Well, it's really down to three things here, which I've labeled here: precision, time, or efficiency, if you like, and complexity. And in some ways, that's sample volume related. So if you want to get the most precise age possible, you want to use thermal ionization mass spectrometry. And this particular plot here, this little image I've got here, is age on the y-axis here, and you've got all your different colored bars, other different instruments that have measured this particular reference material, this particular zircon standard. And it's been measured by ID-TIMS, and the height of these little bars is how precise something is. So the smaller that bar is, the more precise that analysis is. So you can do it by ID-TIMS, you can do it by multi-collector ICP-MS, you could do it by shrimp, you could do it by another multi-collector but using a different collection system, or by what we call a single collection or quadrupole system. And if you take a weighted mean of all these, you can see this sort of shaded bar that you get across here. The height of that bar is that precision. Another way of looking at this sort of data is by plotting it on what's called a Concordia diagram. So you plot both isotopes of uranium over both isotopes of lead. And again, you want to be sitting on this, what looks like a line here, but it's really a curve. And again, you can see the different colors here match whatever you've got on the screen. So you can see your ID-TIMS analysis from these tiny little dots. And if you look carefully on these plots, you can get the weighted mean of that uncertainty on there. So for example, at your worst end, we're all accurate. Every one of these techniques is accurate. You're all getting the same mean, if you like, 550 odd million years, but your precision changes. Here you've got 2.7 million years of uncertainty, right down to ID-TIMS where you have 0.08. So why don't we all do TIMS? Well, that comes down to time and in some ways complexity. TIMS you can do if you're on the ball, sort of half to one analysis per day, if you include, and that excludes things like sample preparation. SIMS, maybe 2 or 3 samples a day. ICP-MS, you can get maybe even upwards of 6. Noble gas spectrometry, things like argon, even less probably than that. So it comes down to efficiency. And so if you are pretty happy with 550 plus minus 3 million years, yeah, go laser ablation. If you want to know exactly when those dinosaurs went extinct, you got to go down the route of maybe TIMS analysis to try and get that right. And the other aspect that comes into play is how complex is your zircon grade, right? If you've got a nice zircon grade that's crystallized from a magmatic melt, it's all the same age, you can dissolve the entire grain and do TIMS analysis on it. You can even do laser ablation. And laser ablation has quite a penetrative volume, if you like, in terms of if you, let's say, use maybe a 30 micron diameter spot to analyze your grain, your pit depth will be almost the same depth. Maybe it's about 20 micron. And that tries to sort of, I'm trying to illustrate that with this sort of grain here. This was an apatite grain that we analyzed. And the diameter of the grain, I think in this case it was, what is this, about 30 micron in diameter. Its depth here is about, about 12 microns. So it's actually a little bit less than what 30 micron is. Compared to a SIM spot or like a shrimp spot, here you're only just scratching the surface, but you're getting roughly the same quality of result. So let's say you've got an Archean grain that's got some cores and some rims. And if you feel like if you're going to stick a big laser spot on it, eventually in 3 dimensions, you're going to drill through the other zone and you get a mixed analysis. And that's not what you want. So thinking of these 3 things, precision, time, and complexity, allows you to determine what technique you're going to use. And again, lots of labs in Australia have 2 or even all 3 capacities to be able to choose what you're going to do. and hopefully they'll know which technique is best for answering your question. The last one I didn't really put on the slide is I say cost. I mean, they're all roughly the same cost, say, per day, the application, but it's how many samples you can get through in a day. So your ICP-MS ends up being, say, a sixth of the price of some of these TIMS analyses. And again, that's something to factor into the equation. Efficiency as well. TIMS requires complex sample preparation beforehand, whereas ICP-MS, you can stick a thin section into the machine and start analyzing things in situ if you happen to have enough material. Now, I'll touch on that a bit more later. So what can we date? Well, not everything. You need to be able to have things like uranium in them. You need to have things like potassium, rubidium. There's a whole range of applications, but you certainly can't go and date a crystal of quartz. It just doesn't have anything that you can date in it. And it also depends on what kind of process you're trying to date. Are you trying to date a magmatic crystallization? Are you trying to date a metamorphic event? Are you going to try and date a gold mineralizing event? And by, say, dating a zircon grain with uranium lead, that might give you the age of when a granite crystallized, but you might have had a gold mineralizing event that came in, 100 million years later. By dating the granite with zircon, you're not going to get that age of that mineralization event. And each of these minerals and each of these techniques has what we call a closure temperature. A good way of looking at it is if you think of your crystals as they get hotter and hotter, their crystal lattices get broader and broader, wider and wider, eventually to the point where a daughter product of lead, eventually if it gets really hot, that lead, which is a relatively large ion, is able to escape out of the crystal lattice. And I've got an image here on the right of using a very small little thing like helium, very small little ion, is able to escape out of, let's say this is a grain of zircon, at a much lower temperature than lead, just because helium is so much smaller. And so you can see that on this plot too. Here we've got, where's uranium, thorium? Here we go, uranium, thorium, helium, zircon. You're looking at a closure temperature of about 180. So above 180 degrees, you're constantly losing all that helium. It's only when you get under 180 that you're actually able to preserve that time, if you like, of when that crystal cooled below 180. You compare that to uranium lead zircon, and you're sitting at upwards of 800, 900 degrees in a normal crystal sense. Now, I mentioned before that we can date things in situ, but that's not always the best way to go. We can date things, and I'll touch on that on the next slide, but one of the most fundamental things we've got to do as geochronologists, and sometimes we skip this step, and I think that's a really poor way of doing things, is we've got to contextualize our minerals in the rocks. The minerals are the building blocks of every rock, and you want to try and figure out what you want to date. Are you trying to date this little stratiform copper gold mineralization? So all these little yellow crystals here, the yellow and sort of goldy crystals are crystals of chalcopyrite and pyrite. And if you look closely, you can see that there's bits of this brownish, it's hard to tell from this image, but there's little brownish titanite crystals that are associated with those, intimately associated with this vein, and not sitting elsewhere inside your sedimentary rock that's mostly plagioclase and quartz. So by dating the titanite, we can date that mineralization. Flip over to the other side. Here I've got a thin section here of a gabbro. So your oranges here are plagioclase, your greens are various pyroxenes and amphiboles. And here we just want to date the crystallization of that sample. And by looking closely, we can see there's quite a lot of zircon in this sample, which would have crystallized late in this gabbroic rock's history, but late as in a magma chamber late. So that would be able to date the crystallization. Now, there is some zircon, but they're relatively small. And will I be able to extract enough zircon in the thin section? Perhaps not. So that brings me to my next question is, do you go in situ or ex situ? Are you able to date things in a round polished block or thin section, or do you have to crush up your sample to try and extract sufficient amounts of crystals out of there? And again, pros and cons for both. Here, certainly you get that, you preserve that textural context, which is absolutely crucial if you've got multiple generations of particularly the same mineral, and it's faster. But it's not always the way to go. And so particularly things like some sort of rare, heavy minerals, like zircon, you might have to crush it up to be able to get your sample out. You're also able to do full optical image characterization. And some techniques like argon-argon or rhenium osmium, you actually need to crush it, because you need to be able to select which grains you want, and you need to be able to if you like, separate them from the rest of the rock to try and unmix. So for example, here I've got these beautiful pristine pelagic clay crystals that have been picked compared to these altered sericite crystals, but they're really sitting in a crystal grain framework like this. So you got to pick out the right crystals that you want. Do you want to date the crystallization, like each pelagic clays? Do you want to date the alteration, maybe the mineralization? Well, let's use sericite. And we can get through a whole series of steps from chopping them up to disaggregating them to concentrating them by gravity techniques and magnetic techniques to be able to mount them and then analyze them on machine of choice. Oops, sorry, my mouse has gone flying. And we, at least at Curtin, have sort of maybe sheepishly branded this as chronotrace, but really it's about taking your samples and being able to take that and understanding what's happening within them, analyzing them, and then timely producing a report of all these different questions. Now, just while we've got a couple more minutes, I might just take you on to a single case study, a little Queensland case study in this case. That is, say, a big project that we had together with Anglo-American. This is still continuing. In this case, it's sort of, we've wrapped up part one, and it's let's say this is a story of not success, but it's a story of conclusive disappointment, let's say. And I'll explain why in just a bit. So Anglo-American were looking for mainly IOCG style mineralization, and they recognized that, look, there's these, in Mount Isa, there's these massive IOCG and other lead zinc deposits. In Mount Isa, surely if you start taking these structures down undercover, so the black outline that I've got here is the actual outline of Mount Isa broadly outcropping. As soon as you start going further south, you're getting into cover. And some, in this case, they were drilling in about 800 meters of cover under rocks that were broadly phanerozoic. You can see there's a lovely trilobite here from some of those, that upper sequence. They figured, look, there should be some giant deposits also undercover. There's no reason why there shouldn't be. So they invested quite a lot of money into drilling 7 drill holes in the western part of the southern Mount Isa terrain, if you look. And what we did is we helped them sort of, they gave us sort of lithological logs. We helped them choose what samples they were looking at. And we got a whole range of ages from granitoids that were intruding from, say, some, if you like, metamorphic gneisses of quite difficult protoliths, some sedimentary rock packages, and some mafic rocks, both intrusive and extrusive. And although we couldn't date everything, certainly the picture that came out is that these rocks were roughly sort of between 1865 to 1755. And if you look at that in terms of, you can look at that, you can complement this sort of, I won't talk too much about this, you can complement this with hafnium isotopic data that's able to help kind of trace your different sources, and you're able to compare the Mount Isa terrain with things like part of the outcropping bits of Mount Isa inlier, and even parts of the Gawler craton, and able to do sort of tectonic wide reconstructions and realize that certain deposits that you find in the Gawler craton and Mount Isa are actually much one and the same. I mean, this is not something that's new, but it's certainly putting this sort of information undercover and realizing, hey, these two things used to join quite nicely before the sort of Thompson origin and other New England origin, all these other Eastern Australian origins came across. But really what they were, in this case, quite disappointed in is their IOCG mineralization sat, and lead zinc mineralization sat in these upper two superbasin sequences, the Calvert superbasin and the Isa superbasin. But the region that we're drilling, at least the ages that we're getting back from the stratigraphy, was sitting more in these two older units, the Leichhardt superbasin and the Kalkadoon-Leichhardt complex. And eventually, after 7 drill holes, based, you know, not primarily maybe, but certainly the geochronology had a large part to do with it. For one, they weren't finding any enriched mineralization. They pulled the plug on this western part of the undercover area and decided to move a couple 100 k's further east. And I've got to keep my mouth shut on this next part, but there is progress at least going further east, and they've drilled at least double the holes now as they have for this first part. So we do a lot of other different projects here at Curtin. We've looking at, say, some frontier copper mineralization, stratigraphic hosted mineralization in East Greenland, looking at multiple gold mineralizing events using, say, rubidium strontium. We're looking at, in New South Wales, we're looking at why some coal seams are cooked and why others are not, and that relating that to sort of mafic sills. We're looking at some hidden suture zones in East Queensland, and by chance we seem to have found the world's oldest magmatic nickel copper deposit up in the Pilbara in Western Australia. So there's some very exciting science that's happening, very exciting things that come across my desk. So just to wrap up, I just got 5 little take-home points. One is geochron is really an underpinning thing. It's, it should be just as important as your structural history, your lithological framework. It's really adding that 4th dimension to 3D models. We've got an enormous amount of analytical techniques nowadays, and that takes a bit of practice to try and get your head around. And each of those has pros and cons. And so knowing what to do, talk to your local geochronologist, and they'll be able to explain it without too much difficulty. But it's quite a complex art nowadays. Hopefully, I've sort of looked at this case study of not success, but of maybe disappointment. But Anglo was able to say, look, we're going to pull the plug here, and we're wasting our money drilling any more holes. Let's move to something that seems to be a bit more prospective. And really, ultimately, and this is what I'm here for, is to try and that geochron, by adding that sort of 4th dimension to your models, helps reduce exploration risk. And that is all I have got for you today. Any questions? I'll stop. Oh, actually, I'll keep sharing.
You can share if you like.
I'll keep sharing.
Thank you for that. That was, I think, a really fabulous overview of different use cases and, comparisons across terrains and that sort of thing. We sort of get used to working in our patch, and then we forget to look beyond that and see the wider world. So really good, especially to hear you talking about things in the Gawler and Mount Isa, and then you're over there in WA.
It's I'd say often it's initiative from when I first took this role in 2019. I was a bit hesitant, as how am I going to drum up business? But really, I've discovered that it's once you sort of get the word out that you've got these capabilities, the minerals industry just comes knocking.
Yeah.
So it's fantastic to see that engagement and to explore for minerals instead of just punching holes in the ground everywhere, just to think logically through, where's the best place I'm going to explore? Where can I best spend my dollar to try and figure this out? And geochronology is certainly just one arm of that, but it's better than just punching holes willy-nilly into the ground.
Yeah, sure is. So Renjie has a question, I think.
Go on, Renjie.
I guess I got, hello, hi Hugo. Thank you for the excellent talk. Just have this question around your comment on doing in situ thin section scanning, for example, and incorporate that into our geochronology workflow. I wondered if you have encountered or have figured out what would be the best approach to do that in terms of saving time and money efficiency type. Yeah.
Absolutely. So we've got at Curtin, we've got a TEMA. You might have heard of a QEM scan before. They're much the same thing. They're a scanning electron microscope that has a whole bunch of X-ray diffraction detectors built on the sides. And what that means is you can take things like a thin section, you can take a polished block, you can take a grain mount, you can take even long, short, thin sections. You can even take some bizarre objects, but as long as they're relatively flat and polished, not cover slipped. I've had a few that have come with cover slips, and that absolutely doesn't work. You can stick it in the machine. It's very low human time. It takes about 20 minutes to half an hour to set up a TEMA, and then your average thin section takes about 2 hours to analyze, an average amount about an hour.
Exactly. Because
go on.
Because I was just going to bring it up. We've got one of those in Brisbane as well at QUT, and I think Elena has been doing quite a lot of work around that. I do think this is sort of a future direction that we need to explore more, how to really take advantage of this new technology and really date what we really need to date, right?
Absolutely. And so these two images that I got here, they're both from the TEMA. Now, I will add, it does not replace good old school petrography, right? There's some things, for example, like muscovite and sericite. You can't tell the difference. It's a chemical technique. So if you've got crystals that have the same chemistry, solid solutions are also a bit of a problem. But if you're trying to find something with an unusual chemistry, something like zircon, for example, not many elements, not many minerals have zirconium in them, you can pick it out, no problem, or some unusual ore minerals as well. Fantastic tool to use to find the little things that would take days to find under a microscope with a person just scanning it. Way more expensive. And for a couple $100, you've got yourself from, say, a rock sample to a report. You've got yourself what's in your rock. And it's always been quite comforting when I do work together with petrographers to see how well it lines up. Obviously, there's sometimes little mineral misclassifications in here that aren't quite right, but broadly, you get it right the first time around.
Cool. Thank you.
That's right. Any other questions?
Do we have more questions? Feel free to pop them in. If not, if you think of something that you desperately need to ask Hugo while the next talk is happening, you can still put that in. Oh, Rick has a question. I didn't see your hand up.
I only just put it up. This is it's just sort of a general question, but it's great to hear that you're doing a lot of work for companies. I'd be interested to hear. So what's the biggest application that they're interested in, and where and what type of thing? I'd be really interested to hear, what's taking up their greatest interest. There's quite a balance, I gotta say. Probably if there's one aspect that takes up more time than most, it's looking at complex stratigraphy. So when you've got particularly Archean and Proterozoic belts that have been chopped up, folded, you often get a lot of lithological repetition, but those lithologies may not be the same state of stratigraphy. When you've got your average, say, like that Anglo-American case, you've got a whole bunch of sedimentary rocks that are, your general sandstones and siltstones that you get everywhere, all that roughly the same lithology. So how do you know what basin sequence you're in? We also get quite a bit on terms of probably the biggest player we get are ones that are looking at gold mineralization. Any sort of hydrothermal systems tend to be the most complex to analyze. And I will add, generally the more mineralized something is, the harder it ends up being, because all those fluids that have come through also like destroying the grains that you're able to date. So generally the easiest projects are the ones where the mineralization hasn't occurred. But the more a rock smells of sulfur, the more I know I'm going to be in trouble because it's going to be hard to date. Thanks.
All right, we have a question from Kriti Bajwaj. I apologize if I've pronounced your name wrong. Question is, how does geochronology help in critical mineral exploration?
Now, when you say critical minerals, I presume you're talking about things like, for example, like indium as a byproduct of, say, sphalerite. So those sort of elements that, I mean, every country has a different.
Let's go with the bigger ones, Hugo. So indium is very valuable, but it's a small market. So things like lithium, rare earths, cobalt.
Sure. So lithium, we've got a huge project here with lithium. We've got several huge projects with lithium here. So a lot from the metallurgical perspective. So we look at pegmatite deposits and look at their sort of continental scale generations in terms of how we explore for them. So for example, just from a WA perspective, we've got quite a large influx of pegmatites in the Archean, but also quite a large portion in the Neoproterozoic. And trying to date these systems gives us, I guess, a wider appreciation of when these systems occurred. I'd say probably most of our lithium work here is more from a metallurgical perspective. Something that we've got other guys here looking at how do we get, say, our spodumene out, our lepidolite out, how do we get that lithium out without in some sort of metallurgical sense, and that's a bit, say, beyond my expertise. But say like I said, indium was a rare one, but there's other sort of novel rare earth element deposits. We've got a project going on with Mount Weld, and say one chunk of that Mount Weld is one of the largest rare earth deposits in the world, and it's in WA at the moment. Well, it's still WA, always be there. But yeah, Geochron certainly forms a focus of that and trying to figure out, there's a big dolerite dike that comes alongside it. Are we trying to figure out, does that dolerite dike have a role to play in when mineralization occurred, or if mineralization really occurred at some economic scales? Did that answer your question?
I'd say it would have. So we might now move on, Hugo, to the next speaker. Thanks you very much. I think that's obviously generated a huge amount of interest, which is fabulous. And unfortunately, we're going to lose Renjie now, who Who needs
I
to go.
will go to teach my students about geochronology very soon.
There you go. Bring on the next generation. So
Thank you, Helen.
show them this webinar. No, thank you, Renjie, for bringing all these fabulous people together. We really appreciate it. Wow. Elena.
Yes.
Let's bring you up.
Yes.
Elena Belousova joined us last year. Was it last year? No, it was the year before, wasn't it?
Yeah, it was 21.
21. Gosh.
Yeah.
So she's been with GSQ now for about a year and a half, and we are so incredibly lucky to have her. And she's going to tell you a little bit about some of the work that's been going on.
Can you see my
Yes. Yeah, we
screen?
can see it.
That's
yeah.
excellent, and you can hear me obviously.
Yeah.
So
Yeah.
I can start.
Go for it.
Good afternoon, everyone. And first of all, I would like just thank you, Hugo, for this excellent talk, and not only this wonderful introduction to what I'm going to talk about today. So I would like to talk about our appetite and our ambition in the field of the geochronology. If I can move to the next slide. Yes, so just to give you just overview of what our main task and projects are. So one of the main project I am involved is a characterization of major deposits, which is a part of our department New Economy Mineral Initiative. And it's not a trivial task, because if you look at the Queensland and these maps, Queensland is a home to many traditional and new economy mineral resources. So characterizing of these deposits, it's taken quite a lot of efforts, and our task is not only to acquire the representative core material as samples, but to create this GSQ reference collection of the mineral system, where we have representation of both physical and the virtual data collection, characterization of the deposits using the hyperspectral method as high-logger, XRF scanning, whole rock geochemistry. We do mineral chemistry. And certainly in this prospect, geochronology takes a big chunk of important work to characterize these deposits. Well, and when I'm thinking about geochronology, it's, you know, my past life. I love my zircons, and I know they're champions. If you look at the one of these diagrams, you can see that zircon is really champion in being used for quite a large number of geochronology papers, because it can be used for the dating of magmatic events, for sedimentary provenance study, for the crustal evolution, and so on, so on. So it's a really, you know, important mineral in geochronology. However, when I started my new job and I got, you know, familiar with the deposits, I just realized that zircons have a little bit of limitation when you're talking about the mineralization system. So again, the diagram you probably saw, remember the similar one what Hugo shows, showing that zircon sits on the very top of this temperature range of the temperature closure temperatures for the different radiometric systematics. So, so if we are thinking about dating the felsic magmatism, that zircon would probably will be very helpful. And when we show the major deposits in the northeast Queensland, there is a significant number of the mineralization system which associated with felsic magmatism, where zircon could be useful. But when you think a lot of this mineralization is probably very closely associated with the later hydrothermal events. So having only zircon, uranium, lead dating would not probably resolve all your questions. But even more so, it's more difficult for the major deposit types which we have in northwest Queensland. Here, the probably significance of this much cooler hydrothermal fluids, which is just associated with this mineralization, is more significant. And in some aspect, in some deposits such as Broken Hill type, of course, the metamorphic events are also important. So when you're thinking about dating your mineral deposits, it's very challenging. You need to think about the series of the events which contributed to formation of the mineral system, starting from magmatic processes, metamorphic in many cases, and the hydrothermal. So we really need the whole range of these minerals and the isotopic system to be able to completely characterize and date these deposits. So what I'm going to go through, just through the different, part of this diagram and thinking in this range of temperatures, what we can use, what radiometric system, radiogenic isotopic systematic to approach and date them. So in terms of igneous, yes, certainly zircon is the champion. We can do both uranium lead and lutetium hafnium. Hugo, thank you again for the good introduction to this. So I put this table just listing some of the minerals. There are probably more than those. And also I have in a table some Australian labs where this analytical work being done, or at least I'm aware. Certainly it's not a complete list, but this is something, just an example where you can start your research in doing it. So in terms of the magmatic, zircon is champion. But if you're talking about the silica undersaturated magmatic rocks, badellite and apatite can be very handy to resolve these questions. And another important point which Hugo brought up, the crystallization age versus the model age. So if we're talking about uranium lead, we clearly get in our crystallization age. But model ages, which we get in from our lutetium hafnium systematic, sometimes very important for our exploration needs, because the source, the prothelite, is critical for formation of some major deposits, such as nickel, porphyry, copper deposits. If you have a juvenile stuff, you are quite more confident go and exploring these terrains. In contrast, if you have the base metal, or if you have your fancy for diamonds, you need to avoid the area where you have a very strong juvenile input. So this is a topic in itself, and I probably would not dwell on it for too long for this presentation. Metamorphic deposits. This is again not exhaustive list of the minerals and the systematic we can use tackling the timing of the metamorphic event. And what is good, we can see we can cover the whole range of temperature from high grade metamorphic events to the low grade. And what I wanted to point out that the apatite and garnet appears quite often in here. And actually this is one of the minerals we are thinking would be really useful for us to look at, because they have also very good potential to look at the trace element patterns and giving us some indication on the fluid conditions, such as oxidation state and so on, so on. So these are just an examples. And finally, hydrothermal deposits. Yes, we also have the same, apatite, garnet, we have biotites, we have carbonates come into play very strongly, and UQ Labs is leading this at the moment. I was also excited to see some development of the fluoride lutetium hafnium dating done at the University of Adelaide. And it's very good sign because in many of our deposits, fluoride is a very common mineral. Well, and finally, there are possibilities to do direct dating of the ore. And we already have seen some of the possibility to do rhenium osmium dating. What I would like to point out that cassiterite was dating, uranium lead dating was developed and successfully applied in the labs of the James Cook University. So I'm looking forward to more close collaboration in this space. Well, now I would like just to briefly go through our GSQ workflow to show how we approach it and how we go through the process of looking at the, whole rock, drill core scanning down to the microanalytical trace element and isotopic studies. Well, and one of the example I would like to show it's our high logger scanning and how it's useful to help us to select the sample and targeting the right mineral for geochronology. So if you look at this example of the summary screen for one of the drill core from the pegment silver lead zinc deposit, you can see there is a brighter interval where I highlighted, which looks like a paradise for the geochronology. It has amphibole, apatite, garnets, mica, and so on. But if you look at the trace and the rock, they're quite gray and indistinctive. And if I wouldn't have this data from the high logger, how easy it would be to miss this spectacular interval and this potential for the dating. So when we zoom in now we have a good handle of what samples we can pick up, and we can now zoom to micro scales. So what technique we currently using? We have a close collaboration with CSIRO and doing the X-ray imaging. Excellent to show us a distribution of elements on the micro scales. And this is one of the example of the SEDEX deposits. But TIMA became a really champion because we have not only distribution of elements, but we have a combination and the different maps, backscattered electron, high resolution maps, and a phase diagrams. And certainly we're looking at the range of methods using a range of techniques, some of them listed here, to get our trace element and isotopic look. So just to focus more on the TIMA, we are really excited, and we have a couple of good successful years. So in the past, we have a good project with the CSIRO where they've done work on the samples from 23 deposits. But now we step in and we develop the collaboration with QUT where they have the instruments, so we can come and do the work ourselves. So this is the example of the same pigment sample which I showed you before in the core, just to emphasize where we have in the thin section scan, we have our backscattered electron image, element maps, and what is handy, you can choose and plot any elements which are needed, which you would like to resolve. And here we can see phosphorus in green, sulfur in yellow, and so on. And then you can see clearly apatite in association, is closest association with this fluoride, and also you have this band of the garnet in association with this fluoride. So you can really target areas and the minerals which are in close association with the mineralization. Another example is more tricky to see. This is the Flying Horse prospect, where this is a copper Mount Isa style deposit, where you have these cross-cutting veins with sulfides and the carbonates. And if we zoom into this area, you can see they're quite large grains. They have over 100 microns, grains of apatite, and they are closely associated with the chalcopyrite in this case and the carbonates. So you have a good target there, and will be quite confident that you are dating the hydrothermal event and the mineralization associated with this hydrothermal fluid. Another spectacular example where we can see rutile, and this scale is 10 microns. So if I zoom in this area of the rutiles, they're quite large grains. They're very suitable for the laser ablation technique. But what I want to emphasize, the usefulness of the TIMA technique, where we can plot a single mineral phase on the backscattered image. So on the phase diagram, you can see it's quite tricky to find these minor important phases, but by using this overlay of the single mineral and backscattered image, it's really make it easy to find this phase and target it with in situ techniques for dating. And the last example I want to show is a titanite. You can see this is the ore sample with sphalerite and galena and a huge titanite grains associated. I don't need even to zoom in, they're enormous, ready to be targeted and dated. Well, so how we going to achieve this? It's a relatively small team. They have recently, just last week, they have a new postdoc. He will be working at the QUT labs to help us with this. But we also have a great collaboration with CSIRO. They still continue doing for us Maya maps. We still continue doing with them in parallel our TIMA imaging. And we really open this collaboration with universities and attracting students to do their master PhD project and work on our GSQ projects. Well, just a few examples of these successful collaborations with university and students. One of the examples we have UQ internship, and Daniel spent 3 months, I think it was 3 months internship, where we had separates of zircons from the igneous rock of Georgetown in Laia. And in these 3 short months, he managed to produce an excellent set of the uranium lead age data on the zircons. And what I should mention that GSQ attempted geochronology of this dating of these zircons, but the results came a bit messy and not very reliable. And one of the reasons, they're very complex grains, they're very heavily zoned, they have a lot of inclusions, and application or combination of the CL images and TIMA mapping really gave us a chance to select the best spot and produce more reliable data. Well, another example, this is a student of Renjie, and she's doing her honors project looking at the fluid evolution of Mount Garnet scan deposit and looking at the range of the minerals which could be possibly targeted for uranium lead geochronology. Some initial, the project is still in progress, but some amazing TIMA images where she identified 2 different garnets with very interesting core-rim relationship. She also have done trace element work and distinguished 3 different generations of garnets. And her initial attempt to get the uranium lead data are very positive at this stage. And also, incidentally, in the same deposit, she found that wollastonite is also a very good potential. It produced some ages, so we just need to think about calibration standard for this particular mineral, which would be very important for the scan deposit and for some other metamorphic sort of related contact metamorphic occurrences. And finally, the last example, which I had a student, a master student, being at Macquarie, and how luckily we choose the project on the Mount Isa, closer to my future work. And she was looking at the some granitoids, and which were suggested, some of them associated with the IOCG mineralization and some of them not. So what she was trying to do, she tried to look at the range of the mineral and mineral system. So she targeted zircons and apatite with uranium lead geochronology and the biotite with rubidium strontium. One of the interesting outcome of this study is that the mineralization related granite showed a really significant age difference in contrast to the others, and in about 200 million years. And this difference is consistent, the younger dates of apatite are consistent with rubidium strontium dating she collected, but also with the ones published from the previous studies. So this is give us some potential to look at the sequences of events, cooling passes for the granitoids through the closure temperature of different systematic. And in the case of mineralization related events, we think we can distinguish two discrete events, magmatic and later hydrothermal, which is more likely related to the mineralization. Well, so just to summarize, to say that we have huge list of the potential minerals and the systematics, and we are really open to hear about new developments, new tools, new application, so we can target our mineral deposits and provide the best possible information in the space of the timing and geochronology. Well, and hopefully all this information will provide useful resources for the industry and improve their capacity to recognize the signature and the halos of these major deposits in the region. So we have a great, task in front of us, and yeah, be happy to go. Thank you. I'll probably stop my sharing.
Up to you. For now, thanks, Elena.
Open for questions.
We have a couple of questions. So, Greg Morrison is asking if there is an up-to-date database of Queensland geochronology data, or is that in the Geoscience Australia database?
Well, no, I don't think we have individual reports, but as a database, I think there may be some files, but I'm not aware of the database. I think we supply our data for the major Geoscience Australia, and there are a lot of data on zircons and argon data available on their websites and online.
And we will always let anyone who's subscribed to the GSQ mailing lists will get an update whenever there's a new report or something like that. We have updates on our open data portal. So we do have a geochronology layer, I think, in GeoRes Glow, but it may not be up to date as well.
Yeah.
All right. Any more questions for Elena? Just pop them in the Q&A, and we might move to Ahmad Redaa. Have I pronounced your name correctly, Ahmad? Good, thank goodness.
Yes.
So thanks, Elena, and welcome to Ahmad. If you can share your screen, Ahmad. He's joining us from the University of Adelaide, and he's going to talk about in-situ rubidium strontium dating of copper gold mineralization. So welcome, Ahmad, and please take it away.
Thank you, Helen. Thank you very much. Hello, everyone. It's great to be here today. I want to start by thanking Renjie. He's not here, but thank you, Renjie, and everyone involved on organizing this webinar. And of course, thank you to all out there for tuning in and listening to our talks. In this part, I'm going to focus on the video extension dating system. I will briefly explain how it works and then what type of materials that we can date using the system. Then I will dive into the in-situ Rb-Sn dating work, which is an advanced technique that has changed the game by allowing us to accurately constrain the timing of different geological events. Then I will show an example on how to use the technique to constrain the timing of multiple events that shaped a copper gold mineralization in the Arabian Shield in Saudi Arabia. And before I start my talk, I want to thank my PhD supervisors, Uri Farakash and Alan Collins, for their support and guidance during this work. Big thanks also to Sarah Gilbert, Stephen Lohor from the University of Adelaide, and to Ahmed Hassan from King Abdulaziz University for their contribution to work that related to the dating the gold mineralization in Saudi Arabia. Okay. Let's start by talking about rubidium. This element has two natural isotopes, which are 87 and 85. Rubidium 85 is a stable isotope, which means it doesn't decay or change over the time. On the other hand, 87 rubidium is a radioactive isotope, which means it releases beta particles over time at constant rate. This rate is called decay constant. For rubidium, when rubidium 87 decays beta, it produces another isotope called 87 strontium, and this is stable isotope, and it's stable isotope among other strontium isotopes such as 84, 86, and 88 strontium. The period that are needed to change the half amount of rubidium to strontium is called half-life, and for rubidium it's about 49 billion years, which means we can use this dating system to date materials that are old as the solar system. So how does it work? To use this system, we need to collect at least 3 samples of whole rocks or any minerals, potassium-bearing minerals such as potash feldspars, micas, clay minerals, and we can use these samples to construct an isochron and calculate the age. The sample is supposed to be formed at the same time. So if we look here, those 4 samples supposed to be formed at the same time, and they have the same amount of strontium, but different amount of rubidium. With time, the rubidium will start to decay, and the strontium will accumulate at constant rate within the system. If the system stayed closed, so at the present time, we can measure the time of the formation, but sometime the system affected by any later events. So rubidium strontium system can be easily resetted. And then in this situation, the clock will be resetted and the samples will preserve the timing of the resetting. How can we calculate the age from the isochron? This is the simple XY diagram, and with accumulation of strontium, the line will move from this point to this point. And if we would like to look at this line, we can describe it using the general formula for the line. And if you compare this formula with the rubidium strontium equations to calculate the age, we will see the strontium ratio, which is in the y-axis, represent the y coordinates. The y-intercept, which is the initial ratio of strontium, which represents the initial ratio of strontium at the time of the formation or the resetting event. The rubidium strontium in y-axis, so it's represented in the equation in this part, and this is the most important part, is the slope of the line. And using this part and compare it with this part of the slope in the line equation, we can calculate the age of the samples. Now the question is how we can get the data. And as Helen and Hugo mentioned earlier in their brilliant talks, there are different techniques. All of them relying on the mass spectrometer, different kind of mass spectrometer. We have TIMS, multi-collector, or the triple quad or single quad ICP-MS. All of these techniques rely on the mass by charge for the samples or for the ions. For rubidium strontium, you may notice that both of them have the same mass. So the normal mass spectrometer in normal case wouldn't distinguish between them. So this phenomenon is called isobaric interference. And we need to separate between rubidium and strontium before introducing the sample to instruments. This process needs to be done by testing the sample in acids and then applying chromatographic extraction to separate between rubidium and strontium, then introduce them to the instrument. This process would take a few days if we consider the cleaning of the vials. But when we finish this process, we can easily load the samples to the instrument and then measure the rubidium strontium concentration or ratios and then calculate the age. Now, what changed the game is the recent development in the ICP-MS by adding a collision cell between two quadruples, which allows us to connect to do the separation online within the machine, and then allow us also to connect the instrument with laser ablation for sampling, and then do the analysis in situ. So if you would like to go to the early work that focus on the online separation between rubidium and strontium, I would suggest Boyle Fernandez work that published in JAZ in 2015. And here I will go very quick on the technique itself. So the idea behind the collision cell is having this reaction cell here between two quadruples, and then when we introduce the samples, we pass all the ions through the first filter here, and we can set up the filter to reject or exclude all ions except rubidium strontium. Then when they go to the second or to the reaction cell here, we can fill this cell with different gases such as oxygen, nitrous oxide, SF6. Rubidium is inert to these gases, whereas strontium can react and produce another product that has different mass. So the detector will detect strontium at different mass. So for example, if we use nitrous oxide as a gas, strontium will react with this gas and change to strontium oxide with mass of 103. But rubidium will stay at mass at 3. So the detector can distinguish between them. So there is no need now for the pre-preparation and extract rubidium from strontium. We can do that online within the machine. If you wish to see what other gases we can use for the separation, I refer you to Hogmullen paper that was published in JAZ in 2017. I will take you to a quick look on Agilent QQQ instrument. The sample can be loaded from here to the plasma. The plasma will break down the samples into the ions, and then the ions will be guided to the first quadruple. And we can set the conditions for the first quadruple and allow certain masses to pass to the reaction cell and exclude other masses that may have isobaric interferences with or may react with the gases and create another isobaric interference. And then the reaction will be conducted in this area, and then we allow ions to go to the second quadruple. We can set up another conditions here, exclude other masses if we wish, and then all of them will go to the detector, which will detect them at count per second, as a count per second. The sampling process will be done by the laser ablation, and the system can pick any minerals or the phases that we want to analyze or date at the microscale. And then we hit these minerals with the laser and create aerosol, that the aerosol will go through, will be carried out by gases through these tubes to the ICP-MS. And then we will get the data. We can process the data offline using, there is different softwares we can use to process the data, such as Lidar, Iolite, Glitter. And then we will get the isotopic ratios. We can calculate the ages using the equations just that I showed earlier. Fortunately, there are now several softwares we can use to calculate the ages. I would suggest Isoplot R, which is available online, or in our software. And using this software, we can calculate the age. Now we will move to Jabal Abla, which is the location that I picked to show how we can use this method in real geological situation. So I picked this area for several reasons. The first one, it's because I'm originally from Saudi Arabia, so this area is in the backyard. And the second reason, the Arabian Shield is unique because it's composed of hard rocks that preserve the history of the Pan-African orogeny, and it's well exposed, and there are many juvenile crusts preserved there as well. So it's a really interesting area. I will start briefly to describe the geology of the Arabian Shield for people who are not familiar with it. So the shield is covering about 600,000 kilometers square, and it's located in the western part of Saudi Arabia. It's composed of several terrains, and these terrains amalgamated around 600 or 550 million years ago. The tectonic setting of the shield makes it like promising area for mineral exploration, especially with the presence of the suture zone that is believed to be the boundaries between the terrains, and also this suture zone has a phyletic composition, island arcs, like the contact between island arcs. In addition, there are several shear zones exist within the terrains, and those areas are known for as an areas affected by deformation, fluid circulation, and this makes them good target for mineral exploration. So I picked this area here in what's called Omfarwa shear zone. It's located in Asir terrains, and in this shear zone, we can see here is a complex of volcanic units. It's known as Schwarzbild, and it showed signs of deformation like foliation. And the Schwarzbild was intruded by several units shown here in orange, and those units diuretic intrusions, foliated, affected by the shear zone. And if I will focus on the area called Schwarzbloten here, specifically this area. So if we take a close look to this area, it's a diuretic intrusion, and it's intruded by several A-type granitoids. I collected samples from the diorite and also from this kind of granitoids. And the blue area actually here is part of this red one, but I highlighted here in blue, just to show it's an ancient mining site for copper and gold. It's called Mount Abla. In Arabic, we call it Jabal Abla. So I collected samples from this area as well for dating and to understand the genesis of the mineralization in this area. So I will take you to a close look to Jabal Abla. So the Jabal Abla is a pegmatitic unit. It's composed mainly of feldspar, micas, quartz, and the mineralization is associated with the alteration zone in the pegmatite, and this alteration zone is associated with quartz veins. From here, you can see it's not clear in the field if the quartz vein is cutting the grisine as well. This unit is a grisine, and this is the pegmatite. But we can see several quartz units here within the within the grisine, which may indicate the re-emplacement of the grisine. So I just collected samples from the pegmatite, alteration zones, and the grisine. In addition to the diorite as a country rocks, and another exposure for the granitoids intrusion in the diorite, just to compare between the ages between those units. Prepared the samples as thin polished sections. So this is the great thing about the in-situ rubidium dating. You don't have to dissolve the samples, just mount them or prepare them as thin polished. This is the holder that we load to the laser ablation. At the bottom of the holder, we can see the set of standards that we use for calibration or quality control. Here we used mica MG. This standard is nanopellet powder. created from phlogobite, and this is another standard we use as primary standards for calibration. We use natural minerals, MDC and GLO, which is phlogobite and glauconite, just to check the accuracy of our data. And this is NIST 610, another standards we use sometime when needed. So the process itself, there is some implication related to the standards and the correction process. I would refer you to these papers and this paper if you want to know more about these implications. But I will back now to ABLA. So we investigated the samples under the normal microscope and we identify two phases of muscovite. The first one in A and B, I would say this is primary muscovite, found in pegmatite and glycine away from the alteration zone. They appear as large euhedral and subhedral crystals. And here I will label it as group 1. In C and D, we can see another group of muscovite. They are secondary, appeared on the alteration zone in the pegmatite and within the glycine. They look small and anhedral crystals. Here I will label them as group 2. I also tested the chemical composition of muscovite using SM equipped with X-ray detector. So we noticed that there is slightly differences in the chemical composition, especially in the iron. The primary muscovite has more amount of iron compared to the secondary muscovite. And in addition to those phases, the muscovite, the secondary and primary muscovite, I dated also the potash feldspars from pegmatite, the alteration zone, and from the diorite and the granitoids units. Here I'm showing the data from potash feldspar dated in situ. The metadiorite or the diuretic unit yielded an age of 651, which is the oldest unit, and I believe that this is the resetting time because this diorite is believed to be 800 million years old. But getting this younger age give us an indication this is the resetting time, and then the cyanogranite or the granitoid unit, the intrusion in the diorite yielded younger age at about 633 million years. And the alteration zone yielded ages ranged between 617 to 525 million years. For the first group of the primary muscovite, we dated this in the glycine and partially altered pegmatite, and the age ranged between 636 611. For secondary muscovite that's formed associated with the alteration, they yielded younger ages ranged between 608 and 598, close to 600 million years. So to make it easier, I calculated the age of every single spot in the previous isochrones and plot them here in the box plot. We noticed that the primary muscovite is the older muscovite, and it's older than the secondary muscovite. And the interesting thing here is that the age of muscovite of the potash feldspar overlap the secondary muscovite and also slightly younger. And now I would say there is two interpretations for this. The first one, the younger age of potash feldspar could indicate that the potash feldspar preserved the lower limit of the alteration event. There is no more intensive study on the closure temperature of rubidium strontium in potash feldspar, and some studies say it's probably about 500 something to 600 and to 800, which is really wide range. And it could be, and this shift could be also related to the matrix effect, as these data calibrated to mica MG nanopowder, which is a phlogobite standard, and it's not chemically matched with the potash feldspar. And this effect can affect the accuracy by about 3 to 5%. And even if this is the case here, the range of the potash feldspar 3%. So if we move it to this way, it will overlap the secondary muscovite. So in summary, I would say that those two phases preserve the timing of the alteration events. Related to the single spot dating, if you wish to read more about this, I would refer you to Rosel and Thomas Zach paper that's published recently in GGR. So to summarize, all the events that occurred in Abla region and formed the mineralization. From the metadiorite, I would say the development of the shear zone started at 680 to 620. And during that time, the emplacement of the granitoid started, including Jabal Abla. The greisenization took place at the later stage of magmatism. And then later, the alteration took place at 580 to 540. The source of fluid, we didn't investigate it, but it's probably the later stage of the magmatism, or probably it's just reactivation along the shear zone, which circulate the fluid and concentrate the copper gold mineralization. If you wish to read more about this work, I refer you to this work, which we published in Journal of Asian Earth Sciences. So to sum up, the in-situ Rb-Sr dating technique is a powerful tool to understand the genesis of ore bodies, but still there is some limitation related to the availability of reference materials. So there is an urgent need now to develop more reference materials, and we are working with Hugo and other institutions around just to develop these reference materials and use them on wider application. Those are the references just as I mentioned. You may wish to capture this screen just if you would read more about this technique. Thank you very much for listening. And yes, please don't hesitate to contact me if you have any question. And of course, I'm happy to take any question now.
Thanks very much, Ahmad. Very interesting. So Helen has had to step away, so I'm going to step in, and Renjie has as well with his course, but we can we can carry on. Do we have any? We have a little bit of time for questions. If anybody had any, you can put them in the Q&A or any of the panelists.
Just a quick question, quick comment, Rick. So the comment about the references on that last slide. So we're recording all of these talks, and we'll share the link afterwards. So in case you missed it, that'll be shared shortly for everyone.
Ahmad, are you trying to? I presume that here in Australia or in Adelaide, you're applying a similar technique to deposits here, or to study areas here. What sort of areas are you working on? Or are you continuing? Is your work continuing mainly in Saudi Arabia, or is it also being applied here?
Yes, I have some projects here. I worked in the last year in a project for the Net Territory Geological Survey, and also I have another project now for here in South Australia, and also I have another project from Saudi Arabia. So yes, working on different projects from here and in Saudi Arabia.
Great. All right. Do we have any other questions for Ahmad? Okay. If not, well, thanks very much, and we'll pass now to Aileen. Thank you very much for getting up early to contribute to our webinar. So we're gonna change systems here to clumped isotopes for clumped oxygen carbon isotope analysis. And Aileen, over to you. Looking forward to your seminar. Thanks very much.
Perfect. Hopefully you can all see the presentation.
Yeah, well, we're seeing the yes, perfect.
Yeah, perfect. I just wanted to say firstly, thank you so much everyone for the introduction as well. And as Rick said, we're in a very different place of the world right now. So I'm tuning in from over in Ireland, where it is relatively early but manageable at 6 a.m. So that's pretty okay. So it's a little bit of a different focus from the talks you've just had. So as Rick said, it's going to be talking about a kind of a relatively novel technique in the economic ore geology world called clumped isotopes. So this is looking at oxygen and carbon isotope systems. So I'm going to not focus too heavily on the theory, but more the application of this. And then I'll bring it back in to link in with geochronology at the end and about kind of some using Ireland as a case study now. So just before I begin, I just want to say thanks. This has formed part of my PhD research a couple of years ago, and there was a huge host of people involved with this project listed here. And this is also linking in with some of the sulfide research as well that we do. And I'll just mention as well, so I'm with ICRAG is the name of the research centre. So we're an all Ireland island research centre that connects all of the Irish universities. And we have a huge host of people looking at not only economic geology, but things like social science and groundwater and other things in sustainability, trying to bring it all together in one place. So this is really one small snapshot of what's going on in ICRAG. There's a huge amount of people doing geochronology work, which I'll kind of introduce a little bit at the end of the talk. But yeah, let's jump into today's talk. So I'm just going to begin with giving you a bit of an introduction to Irish exploration and geology, as I doubt many of you are super familiar with it, and using the Sheen mine as an example, as a case study to walk through the clumped isotopes, and just really talk about things like fluid evolution and sources and mixing, but how all that's really relevant for things like ore geology models that obviously geochronology can help a lot with. And then I'll just talk a little bit about some current work as well. So I just thought this would be useful in case anyone's not super sure where Ireland is. We're a little bit far away from Australia, small little island, but quite an active geology scene. In terms of our exploration and kind of mineralization, a lot of people kind of have this impression that Ireland doesn't really have a lot of mineralization and other things, but it's actually, it's a lot of mineralization, lots of different deposit types. It has one of the biggest concentrations of zinc per square kilometer, I think, or something like that. It has one of Europe's biggest zinc mines. So it's just really, really active. But overall today I'm going to be focusing on the zinc lead mineralization in Ireland, which is probably one of the bigger industries really, but we actually have some potential VMS deposits. We have huge amounts of gold, especially in Northern Ireland, which is part of the UK. We also have a lot of pegmatites as well in Ireland, and there's a lot of active exploration for these. So this kind of research and trying to, how can we make it more efficient in terms of our exploration is really important. So we work really closely with the different exploration companies in Ireland. And I just wanted to kind of quickly introduce, but I'll go into geology in more detail in a minute. But basically the light blue phase here is the one that we're going to be talking about. It's lower Carboniferous Mississippian, known as the Walsorian Limestone Formation. And this is the host of basically most of the Irish zinc lead mineralization that we're aware of. So at the moment in Ireland, there's been 5 carbonate hosted zinc lead ore bodies mined in the last 50 years. And there's about over 20, that's probably actually more than over 20 sub-economic prospects discovered. Huge amounts of zinc lead, and at the moment we have the Tara mine, or it was run by Boliden, and it is a huge deposit. It is by itself is the only operational mine in Ireland. It is one of the biggest suppliers, until recently the biggest supplier of zinc in all of Europe. It is a huge resource, and they actually just found or announced and are currently exploring a new deposit out in that area as well. This really is just to give you an overview, not much else to be taken. It's just a kind of a summary of some of the kind of tonnages and the grades that people have taken from different exploration efforts. But I just kind of wanted to say quickly about some current exploration. And so there's lots of different information here in terms of like finances and different like deposits named. But really important thing is that these deposits are moving to a much deeper level really now. And so we need to have these new thinking and new ways of approaching this to help us basically find these deposits, because they're getting more difficult to find. And traditionally people have kind of always focused on one stratigraphic unit in Ireland, but really we're starting to see potential for deeper resources and trying to understand that from lots of different perspectives. And Tara Mines here, I think it's really worth highlighting that the new deposit or like prospect I mentioned is almost at 2 kilometers depth, and it's a huge resource. It's really impressive. It's really worth checking out if anyone wants to go. It's called Tara Deep. But also we have a new announcement as well, where Galmoy Zinc and Lead Mine, which was previously opened and closed, is actually reopening as well, because there's a huge kind of reinvestment in zinc in Ireland as well. So it's really nice to see the de-risking of exploration happening. So that's really exciting that that's about to open. That's really close to where we're going to be talking about today. And just to finish up our introduction to Irish exploration, it's a really exciting time, I think, to be in Irish geology, because there's a huge movement to identifying other carbonate-hosted systems that have traditionally been called other types of deposits that are actually much more similar in terms of Irish lead zinc. So if anyone has come across Irish lead zinc, you've probably heard it referred to as an MVT type deposit. It's not, it's more transitional between MVT and SEDEX. There's similarities, but it is a different system. And so there's a lot of kind of new identification going on, in particular in like some of the kind of locations here, some in Australia, some in Canada, North America. And so it's really starting to reevaluate the deposits and what we think we know about them. So moving on to the geology, which I know a lot of people will be here for. So as I mentioned, this is just kind of a snapshot of the middle of Ireland where a lot of the mineralization is focused. What's not shown here is we actually have the In-situ where two continental crusts came together, and so that obviously is related to where we get a lot of the mineralization. So the blue is what we call the Walsortian limestone formation, which is Mississippian marine rocks, and these limestones deposited during a marine transgression. But other point that's really important here is that that lower carboniferous, lower Paleozoic basement, that's not meant to be carboniferous, lower Paleozoic basement rocks are thought to be the source rocks as well. So that's really important in terms of metal, understanding metal sources and movement. Really important and nice to point out here that the carboniferous basement here, it's limited deformation relatively, and so that's quite useful in terms of it enables us to study a lot of other features in a lot more detail than say some more altered counterparts in other places of the world. So it's a really good place for getting our baseline fundamental understanding of these systems, and we can look at things like original textures and minerals, fluid compositions, and start to understand the effect say different buffering has had on a fluid and like how that could have occurred. And so that's a little bit of what we're going to be talking about today. And yeah, this is kind of mentioning this, it's a little bit easier to study in some parts of Ireland because it's less deformed and less messed up, basically. And so we can learn a lot of valuable lessons to apply to elsewhere as well. And also the limestone, so the limestone host, the Walsortian limestone formation, this was dolomized on a regional scale, in particular in the south, where quite a lot of those deposits are found. And there's this area locally called Rathdowney Trend in the Southern Irish orefield, where quite a lot of these deposits are found, including the Lachine deposit we're going to be talking about today. And what the Rathdowney Trend actually is about a 40-kilometer northeast trending zone of regionally dolomitized limestones that has structural features throughout. And this regional dolomitization was a really important part for later zinc lead mineralization and helping focus where that occurred. So it's really important to have a better understanding of that as well. Just pointing out here with the purple box, this is where Lachine and that other mine Galmoy is found. So they're quite close to each other, really. And yes, just to point out, a lot of these systems are fault controlled, so we find that mineralization adjacent to normal faults as well. So it's actually quite a nice system in that way. And as I mentioned before, exploration is really moving to these deeper levels. We really need new ways to help us vector towards mineralization. And yes, the Lachine, as I mentioned, is the case study for today. So this is just to give you a quick snapshot of Lachine. So this is just the ore projection to surface. It's all hosted in the Walsortian limestone, except anything highlighted in red there. We won't be talking about that today. But just kind of in summary, Lachine was operational for over 15 years. It only closed in 2015. Strongly controlled by an extensional left-stepping relay ramp fault array, and there's some really nice papers such as the kind of all one listed there in Dorman's one that kind of look at the structural influence on metal distributions as well, and kind of undoing that structural framework. And then quite a lot of the work has really focused on the main zone and the Derryville ones here listed here. But more recently, we've been looking at things like the island pod to look at it because it's less deformed in some places near these feeder faults, and to try use that information to understand the textures that we're seeing in these more complex deformed areas of the mine. And I'm not going to be talking about the sulfides, but I think it's important to introduce them since we're talking about a mine here. So generally we have pyrite, sphalerite, galena, and then we have lots of other phases. Definitely some not listed here. We have a lot of kind of like sulfur salts as well, multiple generations and textures of all of these. But in general, we have this early iron event after that regional dolomitization event I'll mention, that leads into zinc-lead mineralization. Really nicely, there's a series of carbonate phases associated with the pre-ore, main ore, and post-ore stages. So it's a really nice record of the hydrothermal fluid evolution throughout the entire system. So typically you find it at the base of the Walsrosian limestone, and this is kind of considered to be the first clean lime or unit that things can kind of precipitate into. And so we have several models of ore formation that are relatively well established, especially looking at like fluid sources and things like that. But we do have a lot of challenges remaining and a lot of key questions still unanswered related to orogenesis, in particular around the sources and potential alteration of fluids, and in particular as well the timing as well of mineralization. So we have a lot of ideas and debates going on about this, but we are still kind of only moving toward definite answers. So what are these models of ore formation if we look at it from a point of view of fluids and the sources? Well, we have a dual fluid source in Irish systems generally. And so this is actually a mixing model where we have our hydrothermal fluids and our bacteriogenically enriched brines. And so we have a dual fluid source, a sulfur source as well. So there's really nice sulfur isotope work for the Irish system that retracts really well the hydrothermal fluids. And so this mixing was trigger for host rock dissolution and subsequent mineralization. And just important for today, I think, as well, because we're going to be talking about this a little bit, the hydrothermal fluids led to the formation of what we refer to as breccia units. So we have black matrix breccia and white matrix breccia. And these are important, in particular the black matrix breccia, because they often form halos around the mineralization. So they can often be quite used by exploration companies to try identify correct areas to explore, or if they're in the right area, kind of. But that was also a really important step in preparing for the massive lead zinc mineralization. Overall, though, the fluids are part of a multi-stage, continually evolving hydrothermal system where we have several generations of carbonate associated with that fluid evolution as well. So it's really nice record of the entire evolution of a system that could be linked in with the sulfides as well to kind of fill in the gaps that we don't have from that sulfide story. And just to kind of talk about the fluids, to show you kind of how they formed, I guess. We have our hydrothermal fluids that typically have low salinity. It's usually, these are the metal bearing fluids, or lead, copper, or anything else like lead zinc, for example, and also our hydrothermal sulfur. And these are usually up to about 240 degrees Celsius, and they come up along these normal faults, and they mix with sinking bacteriogenically enriched brines that are high salinity and sulfur rich as well. So where these mix is generally where we get that kind of sulfide deposition represented here. So just kind of to point out that a lot of the traditional work has had that dual fluid source, but some more recent work has indicated that there could be some minor influences from things like replacement of earlier pyrite and then local geology variations that account for things like maybe nickel distribution patterns as well. So this could be maybe unknown mafic deposits under deposit and things like that. So that work is it's not going to be discussed today in any detail, but just thought it was worth pointing out as well because it shows that local variation is really important to try to understand as well. Not going to go through this slide. This is just kind of for your reference in terms of some of the questions left to answer. They're relevant for this work. Just wanted to point out in particular about the timing of mineralization. So obviously geochronology, that's something that we're interested in. There's been a long-standing debate in Ireland about the timing of mineralization. Sometimes the same deposit can have two times, or like two forms indicated, so syngenetic or epigenetic. So there's a lot of debate around this in particular, and that has really big implications in terms of exploration, especially in Ireland, because if it's syngenetic, they're probably going to focus on the Walsrosian limestone and that stratigraphic unit, where if it's epigenic, it could be across multiple different stratigraphic units, and we could be missing huge varied resources, which would be amazing, but we'll see. So yeah, just kind of wanted to highlight that a little bit for you as well. So today, going to talk about carbonate phases associated with mineralization, looking at their formation and implications for orogenesis. But before we get into that, we kind of need to understand what the carbonate phases are. So here we just have some representative images, really just kind of want to introduce these. We won't spend too long on this, but kind of the main ones here are, we have our Walsrosian limestone, so undolomitized to partially dolomitized. Then we have what we call Dol 1, which is Dolomite 1, which is actually dolostone. So this is the regional dolomite dolomitization process, and that can be classified into A and B, so we get white and grey forms as well. And then we move into our hydrothermal breccias. So these are called Dol 2 and Dol 3. These are really important to kind of just remember, in particular the Dol 3. There are some challenges with working with Dol 2 that I'll get into in a little bit, but these are all followed by several carbonate phases of calcite dolomite that cross-cut through veins or infill as well. There are some other phases not listed here that we're kind of only starting to identify, say ones associated with lead zinc mineralization that we're hopefully going to start doing some work on, but this is just kind of a general overview to give you an idea. And so I'm going to just quickly mention why carbonates. So I think a lot of people have an understanding and appreciation that carbonates are really important, especially when you're working in carbonate hosted systems. Closely associate mineralization, and they hold a huge amount of valuable information that we can take away and use to help exploration. So in Ireland in particular, we have our pre, main and post-ore phases that record the entire hydrothermal evolution. So it helps us improve our understanding, including sources or formation and mixing and things like that. But also there's a lot of potential as an isotopic vector as well. So we have these large halos of carbonates, and so there could be potential targets for exploration. Now, traditionally, when looking at carbonates, a lot of people will go to oxygen carbon isotope systems and fluid inclusion thermometry to study temperature, formation of fluids, sources, and carbonates. But for anyone who has ever done that, there are a lot of challenges with those techniques, in particular with fluid inclusions, which I think if anyone has done them will understand that they could be the bane of your life and awful things. It could be great too, but in Ireland in particular, they are often much too small, deformed, ruptured, or absent. In particular, that B&B unit, the black metric breccia, generally does not have any usable fluid inclusion. So the temperature kind of indications can be really difficult. We can be missing huge amounts of information as a result. Then with traditional oxygen-18 isotope analysis, this can be used in combination with other methods to get a kind of a temperature reading as well as fluid composition, but there's an element of that where you basically have to guess, or an educated guess, shall we say, to kind of get that. So there can be a lot of human error associated with these techniques as well. Here are some existing fluid constraints as well from Dr. Steve Hollis. I'm not going to spend too long on this, but it's really just to show you an example of how variable the fluid inclusions can be. If you look down here on the right, they're not really nice to work with. But again, the kind of the challenges around that we only have one fluid inclusion for B&B. It's not from an ore body, and then often a lot of other phases are just too small, or just the samples are just too dirty, and it just doesn't work. Regional dolomite as well rarely have inclusions that you can work with. So what are the solutions? How can we overcome this issue and start to infill that missing data and get a better understanding of our entire system? Well, clumped isotopes. I'm not going to go into detail about this. I think the main thing you need to know is it's a geothermometer, basically. So it's a way to get reliable information for the formation temperature of carbonate minerals. So traditionally this has been used in low temperature systems like paleo kind of climate studies as well. And so this kind of application to hydrothermal and like higher temperature ore systems is really a new kind of emerging field. And there's been a good few publications in the past couple of years, but there's still a lot of challenges to overcome, and there's still a lot of important information you need to kind of test if clumped isotopes is useful and like kind of helpful in systems. So what are they? So again, not going to spend too long on this. Not everyone likes isotopes, but basically this technique depends on the ordering of heavy isotopes. So here's just kind of a graphic to help explain that a little bit. But really the main thing you need to know the degree of bonding or clumping of heavy isotopes like oxygen 18 or carbon 13 in carbonate minerals is temperature dependent. So that's really crucial for this method as well. Other things kind of a note here that are really useful to know are clumped isotopes are independent of fluid isotope composition and carbonate mineral chemistry. So you don't need to get the fluid inclusions to get temperatures. Clumped isotopes also result in both carbonate 13, oxygen 18, and temperature. So you get these simultaneously, and it provides independent measure of carbonate crystallization temperature. And this means that we can directly get fluid compositions over modeling as well. So that's really important when we're looking at this. But really the main takeaways before we get into the data of it all are this method can be applied to any carbonate phase, providing independent measure of carbonate crystallization temperatures, which is really valuable for helping with orogenesis studies. So this means that we could get a temperature profile of the entire system as well, and potentially use it as a vector toward mineralization. Not going to lie, there are some challenges, shall we say, in the exploration application. These are being worked on. One in particular is the issue of sulfides, which is a bit awkward when you're working in sulfide systems. But that black matrix breccia is probably the best example where it's actually sulfide rich, which is the main reason that we can't run it. However, my PhD supervisor, Steve Hollis, did try to run it and has a really interesting graph showing contamination for a couple of weeks after. So it's really important to consider sulfide contamination in your systems because it's something that isn't always looked at and it's not always fully known, but it can influence your temperature as well. Now, more recent applications in higher temperature systems like the Copper Belt in Zambia are showing that things like chlorine and salt as well can have an influence. So this brings up the issue and the important point of having this kind of pre-processing stage. Like these issues don't mean that you can't actually run them. It just means that there's going to be probably another prep method to you running your sample. And so just in case anyone is interested, these are clumped isotopes are measured from the dissolution of powders. So it means you have to drill out your carbonate phases. Just really wanted to show this quickly because I think it's a great representation of the value. But you can see so much variation on a thin section scale if you have the right thin section, obviously, or in this case billet. But these are several of those different phases from like before mineralization to post mineralization, and you can track the fluid evolution and the temperature variation on this one scale because of all these lovely interfaces. But what does it actually look like when you step away from that thin section scale and look at this from a deposit scale kind of study? So we did some pilot work looking at the clumped isotope studies of the Irish orefield. Now, my work I'm going to be showing today really stems off the work of Dr. Steve Hollis, who's a lecturer at the University of Edinburgh in the UK. He did quite an extensive work across Ireland, and he also did a huge amount of comparing clumped isotopes to fluid inclusion temperatures to test the validity of the method. And it was quite positive results, and that publication is going to be out quite soon. So yeah, I think it will be in the next couple of months, hopefully. And it's really exciting to see the outcomes of that as well, because there's also a lot of other information that are relevant to the larger carbonate isotope world. So here's the data. So what we're looking at here is temperature versus oxygen 18 fluid. So this is showing all of those carbonate phases that we have data for, but also importantly, we have our two end members here. So our carboniferous seawater and our basement as well. So this is lower Paleozoic basement. And this is really nice because we see this trend basically between these two end members as well. And what's really nice about this is the curved nature of this trend suggests buffering of the fluids occurred due to dissolution of that early regional dolomite or dolostone. Also really important as well, that's not really been considered before, is the limestones, which are all of these blue spots up here are not where you would expect them. And so suggesting that the limestones here are reset, and that's really bringing up an interesting question as well, because that kind of resetting in carbonate and clumped isotope world is only starting to be understood. And so it's really exciting time to be working in the clumped isotope field as well. But really what this is great for showing is that we have this overall trend toward hydrothermal fluids becoming more equilibrated with the basement as time moves on. And I think relevant for people from industry here today are the potential applications of this as well. So there's strong potential for potential vector or pathfinder to ore, but a lot more work needs to be done on this in terms of testing the spatial distributions to identify any temperature trends and known mineralization. So we need to look at samples much more distally as well. That might not potentially work because there's sometimes more altered carbonates and things like that. So it really kind of depends on the system you're in as well. But we can help in understanding isotope resetting. And this is obviously something that's kind of an ongoing area of discussion in the carbonate world. And this shows the importance of using multiple isotope techniques and other methods to really help understand your data set as well. So it's kind of different perspectives to help understand what you're seeing. But overall, early carbonate phases we see are part of this multi-stage hydrothermal continuum with buffering and modification from mixing and dissolution of host rocks. And this is really important because we didn't fully have that information before, so this is helping us understand the kind of full picture of what's going on in these carbonate systems. As I mentioned, there are still several challenges to overcome and contamination preparation, but there's some really good work. The people that we work with are based in the UK and the University of East Anglia, and they're really, really aware of the issue of contamination as well, and they're really, really good to work with. But as I mentioned, it's really important to start combining this with other methods as well. So some potentials are things like uranium and lead dating, and also things like laser ablation, ICP-MS, to gain that renewed understanding of hydrothermal systems. And I say watch this space because since being asked to give this talk, we've actually started to look at potential uranium lead dating of carbonates associated from Lachine, because this has been set up recently in Dublin and Ireland through one of our partner universities. And so it's really exciting to be able to test this method and kind of well-characterized system, see what comes out of it. So I think most of you are here for geochronology, so I'm going to have at least one slide on geochronology. So there has been a good lot of work done in Ireland, and there's lots of past studies, and that help us in particular in terms of the timing of mineralization. But what does that actually mean in terms of implications for ore models? So mentioned at the start that issue of syngenetic versus epigenetic in Ireland. There is some recent work by Danny Nashin, who until recently was based at ICRAG and is now over in Canada as well. So he did some rhenium osmium dating of early ore stage pyrite from Lachine. And so he was able to get an early Mississippian rhenium osmium age. So I've mentioned I'm not a geochronologist, so please don't ask me a question about this graph, but the paper is really great where I read, it's in Nature. And just to point out, this is kind of indicating that sulfide mineralization occurred roughly within 15 million years of host rock deposition, which here's the kind of suspected age range. And so kind of one of the main conclusions of that paper is that zinc lead mineralization at Lachine in particular occurred during the later kind of depositional stages of the limestone, potentially during deposition of some of the overlying stratigraphy, but relatively close to the paleo seafloor. And also this is kind of a protracted episodic mineralization, which is really nice actually, because that's confirmed by some of the pyrite chemistry studies that we did, where we have this kind of early pyrite phase that's showing the episodic nature of the early hydrothermal fluid as well. So that's some of the other work I did in my PhD. And also exciting, this has been confirmed by some more recent work looking at the apatite dating and hydrothermal breccia samples, so in particular that black matrix breccia sample, and this is currently in press with economic geology. And so another just kind of key outcome of that work was that the rhenium osmium ages overlap with volcanic rocks, and they suggest a genetic model involving some magmatic heat as a driver for regional fluid flow. That's still kind of being debated a little bit, but it's nice that we're starting to refine our genetic models a lot more and kind of get that refined understanding to help with exploration and help us kind of guide where we should be looking. Just to kind of quickly point out as well, some other dating studies going on in the Irish orefield. Previously, there's been some work with paleomagmatism, sphalerite, rubium, strontium, carbonate, uranium lead I mentioned, and there's definitely a couple of others not listed there. But one important thing, we are missing that kind of representative carbonate data set. So this is work that we're about to undertake here in Ireland as well, looking at uranium lead carbonate dating. Well, first we have to see if it will work and if we have what we need in our carbonates. But we're also about to look at rubidium, strontium dating of sphalerite and potentially carbonates associated with the really first stages of mineralization, which would be really, really useful to get some data on. So again, watch this space. In a year's time, who knows what geochronology data we will have. I think it's just really important though to point out where geochronology kind of fits, and I'll go into this a little bit in my last slide, but I think it's really important to combine multiple methods, and it's really important to have that characterization. We need to know what we're looking at as well, and I think a lot of times that might be kind of not as focused on, which it's really important to have these kind of multiple perspectives so we can help understand not only the data, but also to improve our orogenesis models and help exploration. So just to wrap up quickly, kind of walk through a lot of information there. Irish orefield, we have our multi-stage hydrothermal continuum, several stages of fluid dissolution altering buffering, multiple fluid sources, and really the main thing here is the clumped isotopes. Using Lachine as the kind of testing ground in Ireland in general shows really strong potential for obtaining accurate and geologically meaningful temperatures for carbonate precipitation and fluid oxygenating values. As I mentioned, there's some challenges, but happy to discuss those a bit more. But it's really just important to combine with other methods like strontium isotopes, which we actually have done to help interpret clump data, just didn't go into today, to help us refine our understanding. And so just before finishing up, I just wanted to talk about some current research. And so how we're taking this kind of work that we did in Ireland and these well-characterized samples and kind of testing ground and applying it to more complex areas. So my current postdoc position is looking at the copper cobalt mineralization in Zambia. So we're applying these techniques and understanding to rocks from the Neoproterozoic, so really old, goes through the drill core in particular that's laid out here is about 1.6 kilometers. It goes through lots of different sedimentary environments, including snowball earth periods or suspected snowball earth periods. So a lot of value to be gotten from there as well. And so geochronology is crucial to this. And there's a huge amount of researchers at ICRAG looking at geochronology in terms of different intervals in this as well, applying it with other methods. And the reason I think it's really important to point out here is because some work that a colleague, Hugo, has done with rhenium osmium dating of pyrites, they got a weird value, so they had to go and look at the kind of the grain, and they saw that there is a lot of variation not fully understood on the grain that influenced the rhenium osmium age. So it's showing the importance of looking at your sample and fully having a characterized sample as well. Hopefully that data will be out soon, but again, geochronology really important. These are a lot of different questions that we're trying to answer in the Copper Belt. Happy to talk about it more, but I'm going to stop and just say thank you for listening. I'll stop sharing my screen.
That's great. Thank you very much. That was really interesting talk. We do have a question in the chat from Andy Brown, who says, I was privileged to visit Navan in 2018, just after the initial discovery of Terra Deeps by John Ashton's group. It's one of the best major discoveries in the last 30 plus years and is amazingly poorly recognized. And I certainly agree with that. So huge kudos to that team. And hopefully, I mean, well, Andy's saying hopefully this isotope work can assist in that future deeper exploration, but it's going to, I'm sure of it. But the question is, have you worked with the Boliden group at Navan testing some of these tools?
So I actually haven't myself, because my PhD was more the Southern Irish orefield. I didn't really go into it, but there's actually a lot of variation between the north and south related, that kind of debasement variation. But my past supervisor, Steve Hollis, actually applied the clumped isotope technique to Navan as well. And so that's going to be in his upcoming publication as well. And yeah, so there's a huge amount of people actually in ICRAG that have worked with Navan and really done a lot of detail from like obviously a lot of petrography and sulfide petrography, but applying carbonate isotope tools as well. So yeah, it's really exciting. I think in the next couple of years, there will be a kind of an influx of publications from the Irish orefield, which would be exciting to see.
We've just got a couple of comments saying thank you. So they're not questions there. I've Anybody else who has questions, please pipe up with them. I'm going to in a second. Oh yeah. Oh no. Yeah. So I've got I was really interested to see the sort of the spread of isotope values associated with your mixing model, because I'm guessing you might have seen that there are similar oxygen isotope patterns, somewhat similar patterns, or at least a gradation associated with, say, matte isocopper mineralization to more depleted O18 associated with copper ore, going out to higher values, varying by about 10 per mil or more with the regional pattern. And I guess my question is there a pattern that you came up with? If there was, I'm sorry I missed it in your talk, where you could say where an explorer could apply that, where they would look at a pattern of oxygen and carbon values and use that as a distal or proximal indicator for mineralization?
So that's actually, I think it's a really good question, actually, because I think it's one of the areas that we're starting to realize that we need more representation from those distal kind of unmineralized areas. So Steve was able to look at the kind of 1 or 2 samples from that, but that's an area we really need to fill in the gaps, because obviously when people do a lot of the work, they focus on the ore bodies, and that means we don't have the reference point for the baseline. So that's something that we've had a lot of discussions about how we can improve and fill in that information. So yeah, to be honest, I think it's something that we really need to kind of apply to and do something and look at those, what a lot of people call boring rocks from far away from the kind of distal samples. But unfortunately, we don't have that kind of the full data set, I don't think.
Yeah, so I mean, to me, it just particularly, the combination of factors there. Well, the first thing I was thinking as you were saying that is like, just imagine, going to a granting body and saying, I'd like money to go out and find the most boring rocks in this basin and measure them. And you go, yeah, well, I don't think so. But
yeah,
I mean, when you combine the sort of observations that you talked about in your research with the challenge of deep exploration and the demonstration that it'll actually bear fruit, I could just imagine a situation where that whole the whole basin, the All-Sortian basin, could be mapped from existing drill holes, and looking at those patterns to try to vector into other ore bodies that haven't been discovered yet.
Yeah. There is some people actually that we're trying to do kind of modeling approaches and like classify, say, different carbonate types. And actually, I should say there's actually a huge resource of like oxygen carbon data for the Irish orefield as well. Some historical kind of things, but there's some challenges kind of with using that data. It's just the clumped method is relatively new there. But yeah, I think actually in Ireland we have this amazing resource of drill core, and we have quite a lot of historical drill core. Lachine was the kind of the testing area, because the amount of drill core recorded is really a lot, to be honest, because a lot of the people involved with that ended up being with iCrag, and we were able to kind of go down and sample and make sure that it was preserved. And the Lachine core shed is actually being converted into kind of an educational resource as well, that will not only host all the Irish samples but anything that people have worked on. So we have a huge copper belt resource over there as well. So it's I think like in a couple of years when that's all catalogued, it'll be a lot easier to kind of pull those samples that we want as well. So yeah, it's exciting actually. It's a good place to test ideas.
I have another question in the chat, and I'm going to sort of paraphrase it a little bit. Based on based on what you've learned, what you know about the Irish ore field, what would you recommend to an explorer as how they would use that information to carry out their exploration?
So I have a bit of I guess that could be controversial answer. I think clumped isotopes has a lot of potential, but it still has a lot of characterization and development to do, and it's also not likely to be as useful the way it is, because a lot of companies are not going to go characterize all their samples and then send them over to the lab, and there's also some lab access issues there. So I think in terms of like the exploration application, that's still emerging. I actually think pyrite geochemistry is where it's at right now, based on some of the other work that I didn't talk about. But one thing that we found was looking at hydrothermal pyrites in the Irish orefield, which are everywhere. There's a lot of issues with pyrite in terms of being used in, like, say, building materials and the effect that's having on houses at the moment. But when you talk to exploration companies in Ireland, they can say that they'll do a drill hole, they'll find nothing in that drill hole but pyrite, a lot of pyrite, and then 5 meters away there could be massive lead zinc mineralization. So it's about trying to figure out how we can kind of move toward that, and like how we can look at that sample that's almost barren and figure out that we're that close to mineralization. And so the reason I think it's actually really good potential is because it's slightly more developed, I guess, as a method. But we're seeing the spatial distribution of pyrite trace element distribution, and in particular in the Sheen, where that kind of was tested. While looking at some of the ore bodies, you see about a 40 to 80% decrease in elements like thallium and arsenic as you move away from the ore body into the immediate subeconomic halo. So obviously that boundary could have changed depending on what day it was drawn, and just depends on the day that the company did it, but it's showing a lot of potential. And we have a current researcher in ICRAG, Claire Giel as well, who's taken that to a much more regional scale and trying to understand pyrites across Ireland and doing some work with like Navan as well. So I think it's actually really exciting time for pyrites as well, but it's also about combining them, I think, because often people will only look at sulfides or carbonates, and they really need to be brought together because they're so closely linked as well. So yeah, I think that's kind of something going. I know that's probably not the answer you expected, but I got converted to pyrites.
And I'm going to ask. I seem to have about 10 questions, but I'm not going to. So the people can keep please come up with a question. I'm going to promote people to panelists in a second, so they don't have to sort of type something into the Q&A. But one of the things that comes up associated with the isotope patterns around some of the sediment hosted mineralization that has some more data in the Mount Isa region is that the ideal thing for an explorer would be to just go and as you say, you don't have to get a sample and characterize it based on detailed knowledge of the ore body that you haven't found yet, which is often difficult to do, that you just want to say, okay, I'm going to analyze the carbonates and hope for the best. But when you look at and look for a spatial pattern, but when you look at, for example, the carbonates around Mount Isa, or at least the older data set that I remember working with, the spread of data, you could see the trend if you looked at the right samples and they were paired genetically right and they were like for like and all that sort of thing. But if you just took all the carbonate data and turned your brain off and just said, I'm going to plot all the carbonates, they were just a big clump where that spatial correlation between mineralization and the halo kind of disappeared, that if you just got a number, you wouldn't be able to tell whether you were super distal or whether you were super proximal. And so the question is there, when you're looking at those individual samples, for example, the ones where you showed that the temperature variation between the paired genetic stages of carbonate in the same sample that was covering a broad temperature range, is there a really broad range of values in that sample that would sort of cover a much spatially broader span that would make it more difficult to use those values to vector towards mineralization, or are they tighter spatially?
Yeah, there's actually been a kind of a bit of a debate around that. A lot of people have used oxygen isotopes and they thought they identified trends where it was kind of increasing or decreasing depending on where you were going on a more kind of regional scale. More recent work has shown that might not be kind of fully representative. I was hoping when we were doing the clumped isotope work, we would see a lovely downhole trend that toward mineralization, you start to see a change in isotopes and temperature, and it's like works really well. But I think in the kind of that pilot initial study, we didn't fully see that. So I think we really need to go back and find the right drill holes and representative samples and test that, because I think there's kind of been a bit of a break almost in the carbonate research in Ireland. So there hasn't been a lot of like publications around it. in like there's the odd one that's not fully true. So like it's there was a lot of like data done in the kind of before the 2000s kind of time, and then yeah, I think there's just a lot more work that needs to be done on it and filling in those kind of more regional scale like variations, because it gets really focused just on the immediate drill holes and the ore bodies and things like that. So I think we're just missing a lot of areas. There is a hell of a lot of people who do a lot of work in some of the other basins though that have no mineralization. And I think we're kind of moving to that time where we're starting to realize we need to work with other carbonate like people and that are not economic geologists and take that value back in. So we're kind of in that transitional stage, I think, where I personally think COVID has really helped in terms of the virtual landscape and starting to work together and try share that information. So we're having kind of meetings with people who we wouldn't often engage with and kind of do that more intercollaboration. So yeah, I guess in summary, I don't think there's a straight answer for that yet, but I think there will be soon.
Great, no, thanks very much. So yeah, there's a follow-up question about the pyrite, the question is there any sort of a relationship you can see? In this case, there was a question about is there any other style of mineralization? Is there like a relationship between pyrite and any gold mineralization, for example, in the region? I know there are some gold deposits, but not perhaps in the basin. Is that right?
Yeah, they're more in the northern part of Ireland. There's, well, no, that's not necessarily true. There are some in southern Ireland, and some of them are kind of there's a potentially really, really large one that's associated with quite a religious mountain, so it hasn't really been explored that much, but it's more Northern Ireland where the kind of gold has been explored more, and there's a huge deposit up there. Sorry. Yeah, that's the one I was just thinking. So that like is it hasn't opened yet. It's kind of still in the stages of working out planning permission and dealing kind of some local issues. But that's a huge deposit and it's gold hosted as well. There has been some people in ICRAG who looked a lot of detail in gold hosted mineralization in Ireland and looking at that kind of pyrite variation and tracing a trace element variation. I've never worked in gold myself. Where I've kind of been more pulled in the pyrite world was a lot of people have used it in VMS systems as well. And also other kind of sediment hosted systems. And there's a lot of potential in other systems to get information out of it, because one thing we saw in Ireland as well is we have this diagenetic pyrite that's usually kind of trace element poor, apart from a couple of things, that records the overprinting almost of hydrothermal fluids that they engage with. So I think there's a lot of potential to go look at other systems and see what's happening with that pyrite, and see if it records influence. I know in Australia there's some really nice, I can't remember the name of the deposits, but there's one in particular I've been told about that like metamorphic kind of grades toward mineralization, and that pyrite's in each of those metamorphic grades and has a potential to kind of record the original information. So pyrite's one of those really robust minerals. I once heard it described as the garbage can of minerals, where it just absorbs all the elements, and I think that's really representative. But it's really, really important to have the characterization. And yeah, the pyrite, like there's a couple of talks on YouTube about it, I think. Or please email me if anyone wants to talk more, because I talk a lot about pyrite. But there's a huge amount of issues when you don't have well characterized samples, because there's so much information lost as well. It's really, really cool though.
That's another, pyrite is another one where, and it has been found to be of use in some cases, but they're also in some of the sediment hosted base metal deposits. You can get the entire isotopic variation in a single sample that you get in the whole, in the whole deposit. So in terms of spatially, really important for thinking about genetic considerations, but harder for spatial mapping. What about when you were looking at carbonates, and you mentioned this briefly, were there any sort of spatial trends in mineral chemistry variations? I know in some of the, I keep talking about the Mount Isa region because that's my happy place, but there's a definite trend in carbonate composition that you can use to sort of move you away from and towards the mineralization, and in terms of manganese and iron content and that sort of thing. So do you see any sort of pattern like that in the Irish field?
Off the top of my head, I'm not sure. I actually didn't do mineral chemistry of carbonates myself. I know some other people did it, but they in the kind of same generation as myself for PhDs, but they looked more at the kind of variation between stratigraphy, and they're kind of trying to look at, say, I mentioned about some of the early replacement textures and about maybe pyrite being replaced and the sulfur kind of being liberated. There's a big question about, say, where the iron goes, and it's likely into some of the carbonates, and maybe like it's a lot of questions I think still remaining around the carbonates, to be honest. I don't think I could definitely be wrong, because a lot of the carbonate people have probably done a lot of work on the more basin scale, and so it's not coming to mind. But yeah, I'm gonna double check that after this talk and include it in the next time I talk about carbonate.
Actually, so I've tried to promote a whole bunch of people to come in as panelists, and they've all been very shy and seem to have knocked back my request. But actually, I had a question for Elena, if you're still there. I see you're still logged in, but then I was going to come to you, Hugo. But Elena, my question was for, you know, in your work in some of the Queensland deposits, is there sort of a, you know, it was really interesting to see that sort of assemblage of approaches covering the range of magmatic, metamorphic, hydrothermal patterns. I've often thought, you know, in a lot of districts, and certainly Northwest Queensland is like this. There's been a lot of texturally based arguments that are, you know, super important to really get the observations as tight as possible, but they've been underpinned by a very, very small amount of dates rather than a lot of geochronological kind of data points. And so what it's made it harder to, or it's to my mind, it's kind of skewed the arguments a little bit, in the sense that, you know, you sort of have one absolute number and then a whole kind of house of cards of interpretation to pin on it. And we seem to have a lot more potential to go in the other direction, where we've got 10 different numbers or 20 that for a deposit or a region that will force our observations into that framework. And do you think that we'll get there with some of the major deposits in the Mount Isa region, or in the Northwest, you know, in Northwest Queensland, where we can use those sort of that assemblage of different geochronological approaches to really pull apart some of the detail of some of these systems in a way that will be beneficial to exploration?
I think this is an ideal world, what we are leading to look at these previous studies where they clearly see the paragenetic relationship. And I think using this in situ information, clearly understanding, first of all, paragenetic relationship. Secondly, using the trace element geochemistry for minerals, just clearly understanding the different populations. And then we can apply our geochronology, so we know exactly where we are in this system. So relative relationship would be very important. Putting the temperature on the top of it, it will be fantastic. But then having the age information, that would be a perfection picture. So we can't, that's why I'm saying the dating of the mineralization system, it's so challenging. It's not a single date. So without the clear understanding of the processes and where these phases we are targeting for the dating sitting in this process, this is the key to answer this question. You can create 10, 20 different ages. You can, then you need to distinguish, are they dating the crystallization event? Is this a model ages? We just talking about the source. Is this something overprinted with the metamorphic event, and the systematic we use was reset, for example? Is it much later a hydrothermal event? So they're all important questions. And we can't just look at one system, one mineral, one date. Unfortunately, it's not that simple. So listening to this clump isotope and temperature, it's a dream world. If we can compare, you know, uranium lead information on the carbonates, plus the clump isotopes, plus our knowledge on the geochemistry, because I can see in many of deposits, you can calcite, just pure calcite. Then you start to get the calcite evolving to anchorite. You have your dolomite, you have siderite, you know, you have such a variety. Just looking at the TEMA data, they're all different, you know. Do they form at a different temperature? Do they come in from different, you know, hydrothermal events? That would be, this would be future. We are in the very early stages, particularly with my experience. I just joined, you know, geological survey and working on this area very, very recently, but seeing all these developments, I think we have a very, very long and interesting way to combine it all together.
Yeah, I just think it's super exciting to add that whole dimension to what's been a very kind of observationally and kind of paragenetically focused, which is very important, but it's so rich to add these sorts of things. Hugo, I wanted to come back to your area, because it feels to me like the example that you talked about from, you know, the southern end under cover of the Mount Isa inlier working with Anglo is really the front line of future exploration, in the sense that more and more we're going to be drilling deep holes into areas where we have very little data, and so many of our tools at those sorts of depths stop working, and you know, the tools that we need to apply are so different. But I guess based on your experience in that one case study, what would you recommend to the next explorer who's gone somewhere and they're drilling for a target that's, you know, where they've got a geological interpretation in the mag data and maybe a couple of holes, and they're you know, they've got enough money to drill 3 or 4 holes, and, you know, what would you recommend to them in terms of an approach that incorporates geochronology most effectively?
Look, I think Anglo did a really nice approach. They went for a really comprehensive tack. They did sort of, you know, whole rock geochem, geochron, obviously an interpretation of the geology. They thought they were sitting in a much younger super basin than they really were. And so, look, I think the biggest things with exploration, and that's a thing to keep in mind, is how quickly can you get that geochron. I think I'm preaching to the converted here, but I think the geochron is a fantastic tool just to be able to figure out that stratigraphic correlation in this case. This particular case study, we didn't really, well, it wasn't really any mineralization, but there was not such a, certainly in some follow-up projects, we've been looking more about, you know, what was the timing of mineralization compared to what the host rock is, you know, was it syngenetic, epigenetic? That just wasn't anything that we could do in this first study area, but anything, you know, drill a few holes, send samples, get the analysis done quick. I think the record we've had in terms of getting an age out to Anglo was 5 days. So we got the samples, made thin sections, characterized them, crushed the rock. 5 days later, there was a report on this. So that was pretty exceptional. Normally, sort of those turnaround times are sort of in this sort of 6 to 8 week mark, and that's, you know, it's sort of working closely together with industry to try and meet their objectives. And in say, certainly in one case, we were a little bit too late and I'd already started drilling the next hole. And so it's being able to kind of do things efficiently while getting good data on the table is really crucial. So if it takes months, and there's certain techniques like argon, for example, that can take sort of multi-months because you need to irradiate a sample.
Yeah.
That's only done every couple of months. And so, you know, sometimes that's not the tool of choice. And that's why I say I'm really quite excited with rubidium strontium, what Ahmed was presenting on, is because you're able to take, maybe not at the precision of argon, but you're able to take a lot of potassium bearing minerals and date them and get information rapidly, right? If you've got a thin section, you can get, theoretically, you can get the answers you want the next day. So I think that's my approach is include geochron as part of your routine exploration, particularly in areas undercover, particular areas where there's complex structural compartmentalization, if you like, in the belt.
Right, thanks. So the we've come up to 5 o'clock. I'm going to have to run in a second, but is there anybody? Are there any other questions from anyone, or any other comments anyone would like to make? Might go around to any sort of closing comments from any of our presenters. If not, look, I'd like to just thank all of you, and as well as Ahmad, who had to step away earlier, for a fascinating set of talks. And those of you who are still online, and there's quite a few, on the 30th of March, our next one of these webinars is coming, and that's going to be the second version of a webinar. First of which we ran last year, called Women Leading Exploration. The first one of those was absolutely fantastic. So we're looking forward to a repeat of that. Looking at the this is a topic dear to my heart, because when you look at the I think it was about 1,600 or so companies out there that are exploring on the various different listed exchanges. There's only about 15 that are being led by women, and I think it's time that some other sector of the population gets a chance to see if they can do better than we fat old blokes have. So I think it's going to be a really good session. So I hope you can come, and I just want to say thank you to Ahmad, who's not here, Aileen, Hugo, and Elena, and say, good afternoon, good morning to everyone, and thank you again for coming. See you later.
Thank you.